In this clip, we're going to look at how to find the matrix of the adjoint of an operator. So the first thing to know is what we want to call the adjoint matrix of a matrix. So suppose we take some matrix A here, and so this is going to be a 2 by 3 matrix of complex numbers. So F is equal to C in this particular case. And in particular, I've got a bunch of non-real complex numbers. So then the conjugate transpose of A is A star, or the matrix adjoint. And what we've done is just taken, so here's the transpose. So now instead of going like 3, 2 minus I, 7 plus 5I, it's 3 and then conjugate of 2 minus I and then conjugate of 7 plus 5I. So remember, conjugate just means you change the sign on the imaginary portion. So here we've got a positive imaginary and a positive imaginary. So coming down, we're going to have a negative imaginary and a negative imaginary. And then, the real part just stays the same. Okay, so the matrix adjoint of A, or the star of A, is the conjugate of the transpose of A. Okay, and now you can guess what's coming. Suppose we have an operator, then the matrix of the adjoint is going to be the adjoint of the matrix. So here I've got everything written out in terms of the respective orthonormal bases. So we're assuming that we've got an orthonormal basis for V and an orthonormal basis for W, and then these matrices are the corresponding matrices with respect to those two bases. But this is going to be useful for the proof, but it's a godforsaken mess to write down. So most of the time, we're just going to assume that the bases are understood, and I'll write this identity in this form right here, which is nice and simple and straightforward. I mean, you would believe that to be true, probably. Okay, so let's go ahead and do the proof. And it's a bit ticky-tacky because we got to work with coordinates and in terms of different bases and everything, but it's not actually too bad. It just goes back, like most of these proofs about matrices, it goes back to looking at the definition of the matrix entries. So let's recall that the kth column. So this is how we define the entries of a matrix. We define it in terms of the entries of a particular column of the matrix of T is the coordinates of the image of T times the kth basis vector. And since this T of EK is now in the codomain W, then we're going to be looking at the basis for W that we have chosen, which is the M's, or sorry, the F's. Okay, so explicitly, TEK is going to be, well, how do we express this in terms of the F's? Well, we have TEK times F1 in the inner product against F1 plus da-da-da-da-da TEK FM against FM, right? Okay, so so then if we want to find the jkth entry of the matrix, so if we're looking at the jkth entry of the matrix of T, then we want the coefficient of the Fj, which is going to be TEK Fj. All right. So now, that's given us something about the matrix of T. Now we need to compare this to the corresponding matrix entry in the matrix of T adjoint. So, meanwhile, back at the ranch, we have T star applied to Fk. Now if we express this in the basis of V, then that's T star Fk E1 against E1 plus etc. T star Fk En against En. So if we look at the matrix of T star and we pull out the jkth entry, then we end up with T star Fk En. Or sorry, not N. What am I saying? J. We want the jth one. Okay. All right. So now I have to relate these two things to each other. So let's see. So I can bring the t to the other side. And then I can flip it, so I have the t in the first one, and I just have to pay with a conjugate. So tej fk conjugate using conjugate symmetry. And let's see. This is the matrix of t entry in the kjth position conjugated, which means then that to get to the other one, to connect the dots here, this is actually now the kjth entry of mt is the jkth entry of mt transpose. Okay. So that's my relation, and that gets me the exact thing that I was looking at. So this is the jkth entry of well, I've obtained this formula for jk. So this is jk, and then that gives us the result.